Welcome back to ECE 320. You have a couple of more assignments before exam number 3, and exam number 3 is in 2 weeks on the 18th of April. And there's also, I've been making fun of this wording, we're on supplements now. In the other class, I've been giving the students supplements for a couple of weeks. You have supplements now for Unit 7 on convolution. These are not 75-minute worth of supplements. They might be 30. I don't remember, but you have 4 such supplements, and hopefully they will help you. And they have some interesting titles. Flip and slide. We're talking about flipping and sliding. We have intervals and limits. Those are the mechanics behind convolution. So if you want to maybe see that a little bit more explicitly, I hope that material helps. We'll go through a convolution problem today, but hopefully those will help you. Then supplement 7.5 talks about low-pass filtering a constant. What does that mean, or what does that do? And then the last one here for a supplement is what happens when you convolve a unit step with a unit step. Those are some supplements you might want to look at. I think they would be helpful in trying to work through Unit 7 material. Today what I want to do, since the power outage kind of messed us up last time, how many of you actually looked at the end of the notes from last class? I added like page after page. Did anyone even look at the notes? Not that I told you to, but we'll go through that right now as an intuitive development of the convolution integral. Then we will look at an example of convolution. And one of the big things I want you to try to keep in mind is that multiplication in the frequency domain does not mean you multiply time domain waveforms. You need to convolve them. Convolution in the time domain is equivalent to multiplication in the frequency domain, and that's probably why you like to go into the frequency domain, is it avoids solving differential equations, it avoids convolution, but in this class we are going to have weird-looking x of t's and maybe weird-looking h of t's, and so it's important that you can convolve those in the time domain. Those may be made-up problems, but they're designed to test your understanding of the mechanics. Can you perform the convolution? That's what we want to make sure you're comfortable with. And then, essentially, before we get to exam number 3, we'll need to be thinking about transfer functions, whether those arise from a passive circuit, that means R, L's, and C's, or active. Active means you have op amps, and you can now design filters either way. We'll look at system response and the S-plane design. Sinusoidal steady-state response, that's in section 7 of the textbook. And then, if you like drawing, and I've heard that there's a strong connection between learning and drawing, graphically determining h of j omega for different values of omega. And if this h of j omega, when you see that, what do you think of? Oh, I was hoping you would say tent, circus tent. So that's really walking up the imaginary axis, and you're looking around as you stop on each frequency, omega, you're saying, how do the poles and zeros contribute to this particular frequency? That's really what h of j, that's one way of sort of thinking about h of j omega, and we'll try to make sure that you're clear on how you could actually sketch that or perform that calculation. H of j omega is going to be a complex number. How do you find that number graphically from our complex S-plane? That we'll need to be comfortable with. I'm going to scroll through this because, as I said, you have this already provided in the end of last lecture's notes. It was after class. We kind of got shorted on our time because of the power outage. But here's the convolution integral. You can use it in either way. And when I talk about flip and slide, that's what you might be thinking about when you see an argument of t minus lambda, either in your h waveform or in your x. You can either flip and slide h or you can flip and slide x. Which one is probably going to be the one that's easier for you to perform the convolution integral with respect to? Typically, I would flip and slide a waveform that doesn't have as much going on. By that, maybe it has a constant amplitude instead of this functional form between various points. That's what I'm meaning by the strategy being to use the integral, either 1 or 2. They both give you the same answer. They look different in calculating those answers, but in the end, you will end up with the same answer at the end of the process. Which one you use? I would say use the integral that requires less effort. And in some cases, you might get halfway through and you go, oh, this is the wrong choice. Well, you might want to just keep going, because restarting may be more work overall. What's the idea that we're trying to capture with convolution? This is the frequency domain version of what's going on. You have a system, and that h of s could be, in this class, it's probably a filter. It's some circuit. But in general, it could be a sensor. It could be an automobile. It could be some mechanical system. It could be a robot. But that's now h of s. That's a system's transfer function. It connects an input with an output. That's the block diagram description. And in later courses, you'll need to be very comfortable with this concept of a transfer function. And that carries over into multiple domains, not just electrical and computer engineering. What we want to do is think about that process not only in the frequency domain. In the frequency domain, the output y of s is simply equal to h of s times capital X of s. And I couldn't not mention this. I was on campus today. Somebody was walking, and I saw their shirt, and it says, "Shift happens." And I just thought of 320, because we talk about just hit the shift key to do the Laplace transform. Shift happens. So this class, shift happens, okay? Hopefully I'm enunciating properly. But here's the output in the frequency domain, h times x. In the time domain, that's going to be convolution. But if we now had an impulse, where x of t, our input, is the impulse waveform, you know the Laplace transform of that impulse. That's just 1. You put that into the definition of the Laplace transform, and you'll find that capital X of s is 1. If you now plug or replace x of s with 1 for an impulse waveform input into this system, the output is just the Laplace transform of the output is just the Laplace transform of the transfer function. So if you want to know what is the output in the time domain, what is little y of t, then you simply have to inverse Laplace transform capital H of s. That's equivalent to inverse Laplace transforming capital Y of s when you've hit your system with an impulse. And we call that the impulse response. It's the response at the output of your system when you apply as an input to that system an impulse waveform. So you kick the system with an impulse, and it responds, that's the impulse response. That's the little h of t in the time domain. And that's what I'm trying to get us comfortable with now. Little h of t in the time domain, that's the impulse. And what does that sort of like? If you apply an impulse waveform to a system, that energizes your energy storage elements, your inductors, capacitors in this class, in certain ways, depending on how those inductors and capacitors are interconnected. And then what happens? You no longer apply an input, it's already energized everything, and then everything just starts exponentially decaying with an RLC circuit. That's what h of t is doing. It's showing you how the system decays after it gets excited. Its initial its energy storage devices are energized. So let's use that to our benefit. Here, this is an arrow on a straight vertical line. That means it's the impulse waveform, and it's weighted with a weight of a sub 1. The area underneath that impulse for x sub 1 of t is a sub 1. If you now applied that signal to a system that had an impulse response h of t, then you know what the output's going to be. It's going to be the impulse scaled by that a sub 1 amount. Everyone comfortable with that concept? We're just kicking the system, and you said if you kick it with an impulse, you get h out. Now we kick it with an impulse that's weighted by a different amount, a sub 1. It's not 1, it's a sub 1. Then all we have to do is scale the original impulse response to get our output due to that input. What happens now if we apply a slightly different input? Again, we're applying an impulse, but now that impulse is at some other time on the time axis. It occurs at tau sub 2. If you hit a system at time tau sub 2, is it going to start shaking at 0? If it's a causal system, if its impulse response started at 0, it's going to start after you've kicked it, or when you kick it, and that's really all we're saying here. We're saying that as soon as you hit the system with an impulse that has weight a sub 2, then you're going to see the impulse delayed by that same amount, t minus tau sub 2, scaled by a sub 2. If you bought the first picture, you better buy the second picture. And now you're comfortable buying anything I'm selling. I hope. Because now, let's go one step further. What if I say, here's a new input, x sub 3, which is a combination of x1 and x2. Yes, so now you just kick it with a weighted impulse hammer. So now you hit it with a higher value, or it could be a fraction. It could have been 1/2 a1, or a1 could have been negative if you wanted. But in this case, now we're just combining x sub 1 and x sub 2. So what are we doing? We're kicking the system with x1, and then we wait a while, then we kick it with x sub 2 after a delay of tau sub 2. And that produces the combination, and I'm not really showing that these are added, I'm just sort of showing you the two different impulse waveforms that you would combine, resulting from x sub 1 plus x sub 2. So it would now just start combining those waveforms together. in time. Now, is everybody strapped in? All right, everybody's buckled in. Suppose this is the input, x sub 4. Well, and now I'm saying suppose that x sub 4, we know the value of that waveform at time tau sub 1, and we're just going to call that x sub 4 at time tau sub 1. Likewise, the center rectangle has a height of x sub 4 at time tau sub 2. Well, we know how to solve it if they were impulses. So let's just do an approximation. Suppose now, and that's what that crazy, it doesn't like convolution either. If you're paying attention at home, we just lost a screen, but you didn't see anything, I'm assuming. But what I was going to say, maybe I shouldn't point to that because things happen when I seem to touch that. There's something strange going on. It's probably electrical or something. But this is the approximation signal or implication that I'm trying to draw. Suppose that now we apply impulses at tau 1, tau 2, and tau 3, and we give those impulses weights equal to the value of that waveform. And now I'm assuming that the height of that really gives you the area underneath that little rectangle, because I'm assuming now they have a width of 1. And we now approximate that and say, oh, we have a tau 1, a tau 2, and a tau 3 are the times that we're kicking our system. And if we now kick them with impulses weighted by the amount of that area of that waveform, then we know how to produce the output. The output y sub 4 is simply a weighted collection of impulse responses. If we hit it with x, and the x is an impulse, y, the output is h. Now if we just have it where we're applying a train of weighted impulses, then that's what we're going to see at the output. A collection of weighted impulse responses. And I think you can see maybe or anticipate where we're going. Suppose we chop that up a little bit finer. And instead of 3 pieces, we chop it up into capital N pieces. Then our y, and now I'm saying it's a little different, so I have a party hat on top of a tilde for y. Y sub 4 is just an approximation of what y sub 4 might be. We're now summing capital N of these scaled delayed impulse responses to produce y sub 4. And you know where we're going. If we just kept going, that finite sum will turn into an integral if you just keep slicing and dicing finer. And hopefully you can see the connection. We have an x sub 4 of tau. That now becomes a continuous variable. We have a shifted in time, in tau, impulse response that we're weighting by the shape of our original input, x sub 4. And we just add all of those up from minus infinity to infinity, and that gives us our output. And in fact, that's the convolution integral. That's what we want to be able to do. We want to now be able to, I give you an x, here's an x, and I give you an h, I have to give it to You have to have both of them. Now you flip and slide one of those. Let's say it's h. You perform this integral and you generate the output y. We want to be able to do that for any x and h. And those may not make any sense physically at times. I may make a crazy h. It may be non-causal, meaning it may start before time t equals 0. But I want you to show me that you understand how to do this mechanically or mathematically, even if h is something weird and x is something weird. Now, it might not be so weird if you're talking images. Then a negative x may not mean as much as relative to causality, but you might want to convolve these images or filter an image. And now your filter has this impulse response. How do you manipulate this image? We're doing signals in this class. And those are just one-dimensional. You're welcome. So they're not two-dimensional. We're not doing two-dimensional convolution. Right? Yes. We're staying in. So now let's look at an example. Here's the example. And we can do it either way. Those two integral expressions are equivalent. They won't yield, or I'm sorry, they won't produce the same mathematics necessarily, but the end result will be equivalent. If you now start doing the first step with the left-hand side and your buddy does the first step on the right-hand side and you compare them, you're going, we are not getting the same answer. Wow, the room doesn't even like convolution, does it? So here are the two waveforms. There's x and there's h. And h should look familiar to us in this case. This h looks like a first-order system response. That's a low-pass filter's impulse response, in fact. So this h of t corresponds to the impulse response of a low-pass filter. So you kick a low-pass filter if it has the appropriate RC product or time constant. What is the time constant here in this impulse response? Did everybody hear that? I'm sure it got picked up on the recording, on the mic. The time constant is 1/2. So practically, when would you expect, if you hit this system with something at time 0 and stopped, when would you expect to no longer have to watch the output of that system? After 5 of those time constants, so you could say 5 tau, which isn't quite right until you give me the tau, which you did, which is 1/2, so it's 5 times 1/2, or 5 halves, or 2.5 seconds. You only have to wait 2.5 seconds, and then you're done watching it. Not a great movie, but it was okay while it lasted. What? It was a thriller. It lasted for 2.5 seconds. But now what we're asking is, what if we applied an input that started actually at -1 and stops at 3? If I now said, okay, you have a filter, just answer this intuitively. I give you a filter, and I say, here's an input, and based on my time axis, where I've marked 0, you're going to start exciting this filter at time t equal -1. When do you expect to see an output from that low-pass filter, or some kind of movement, or some kind of response? Did everybody hear that? So I shake it at t equal -1. It's going to start moving, isn't it? At t equal -1. It's not going to wait, because that's what this says. This says you start me at 0, I'm going to start shaking. So the fact that this starts exciting the system at -1, you should expect something non-zero happening in the output at time t equal minus 1. What we want to see is, okay, I put this in. Now think this through. You put in this square pulse into a low-pass filter. What would you expect to come out of a low-pass filter? Now you're saying low-pass filter this square pulse, and this might be an interview question. And they say, okay, oh, you've had 320A? Here, filter this pulse. Can I come back? I'll come back next week after Tharp's told me how to convolve this, right? But if this impulse, if that filter looked like an ideal impulse, and how would you do that? You would make it much faster. So this would go really high, and then it would be exponentially decaying very fast. So your time constant would be really short, and now you're saying the bandwidth of that low-pass filter is quite large. If this impulse response looks more and more like a true impulse waveform, the output's going to look almost identical to the input. But because this doesn't really look that much like a pure impulse waveform, does it? Then we're going to distort this. We're going to smooth. For some reason that echoed to me, but maybe anyway. We're going to smooth these sharp curves. We're going to round off this high frequency content in this signal. We're going to kind of do this, and then we'll do this. Do you see that? I'm sorry, you can't see that if you're listening to this. So let me try to tell you what I just... You might see something like that. And then when it quits, well, you're not seeing anything with the screen going black, but that's what you might see. And if you had a wider bandwidth on your low-pass filter, instead of maybe seeing that yellow, you're going to see something even more like the square pulse. Now it might do... Do you see the difference? Question?
So the rising and falling slopes are the same, but in the flip, so it's like it's the same curve, just flipped over the horizontal axis.
So now I think you're asking, when it sort of smoothed at the top and then it smoothed at the bottom, the one is if you excited this with a constant, it's going to exponentially go up to a steady value. That's what I'm showing on the left. That curve shape is still influenced by the same mode. In this case, it will be e to the minus 2t. And you'll see the same kind of decay shape when it's shutting off. I'm not sure if that answered your question, but I think your question was, how are these shapes, and my drawing may not be accurate, but how is the shape going up related to the shape going down? And they have the same exponential characteristic.
So is this
So is this representative of an RC circuit? It is exactly an RC circuit with the appropriate R and C. You give me an R and C that gives me an e to the minus 2t mode, so then what would that be? Now your RC, you would say e to the minus t over RC. RC equaling 1/2 would give you an e to the minus 2t. Your time constant was 1/2. So you give me an R, so go see Josie and ask for a capacitor of 1/2. See what happens. Actually, now they do have big capacitors, but the product of R and C needs to be 1/2 for this. This is a made-up problem. But it is an RC circuit. Can be. All right, we need to get going. We want to convolve these. So now we want to convolve H with X, and what we're hoping is we eventually see this yellow or blue highlight depending on what our H of T looks like. So we want to find the output, which this is the output. or the blue is an output, depending on what h of t looks like. Those are two different outputs depending on what h of t looked like if we varied h of t. Which of these two waveforms do you think I would prefer to flip and slide? I would prefer the left one because it has a constant value. This one has a functional form, and I need to flip and slide. That gets a little messy. So let me flip and slide x in this particular instance. But either way will give you the correct answer if you do it properly. So what I need, if I'm flipping and sliding x, I'm working with this first integral after y. I'm going to say x of t minus lambda. I now need to find h of lambda. Huh, that's a piece of cake. He gave me h of t. I just have to replace t everywhere with lambda and draw it. So I can find h of lambda pretty easy. So let me write that down. And I'm going to do this in multiple steps. So now I need h of t. Bless you. So here, oh, I need h of lambda, don't I? So there's lambda. This was 2, and here is h of lambda. This is now 2 e to the minus 2 lambda. That comes directly from h of t. But I need that. That's going to be one of my waveforms in the argument of these integrals when I start computing them. Now, I need x of t minus lambda. And I'm going to do that in 3 steps. And I would encourage you when you're first doing this to do it in 3 steps. I'm going to first find x of lambda. Then I'm going to flip it, x of minus lambda. And then I'm going to allow it to slide. T is going to be a variable, so I'm going to introduce a t. Those are my 3 parts. I'm going to look at x of lambda, then flip it, x of minus lambda. That gives me most of it. And then I need to allow it to slide with t as a variable, and I'll introduce t and create x of t minus lambda. X of lambda. That one's not too hard to sketch, hopefully. Here's lambda. X of lambda. And my heights are not going to probably be consistent, but let me just say this is now 5. This is now minus 1, and this is 3, and that has an amplitude of 5. That's x of lambda, based on what x of t was when it was given to me. The next step in this process of flipping and sliding x is to flip x of lambda. That just means flip it around the vertical axis, lambda equals 0. I'm just creating x of minus lambda. Or, keeping that picture in mind, up in the upper right-hand corner, I need to flip it. So now the minus 1 becomes plus 1, and the 3 becomes minus 3. The height is still 5. Hopefully you guys can draw better than I can. And this is now minus 3. This is x of minus lambda. Everybody understand where that, or how to find x of minus lambda? Now we simply introduce the sliding variable, which is t. Lambda is our variable of integration. T is the one that we slide around, or use to slide x through h. Now let's create x of t minus lambda, and it's easier to just assume as you're sketching it to make t really negative in the sketch. I'm going to now put t in on all of these places for x of t minus lambda, And what that will do is it will say, oh, this endpoint is t plus 1, and this endpoint is t minus 3, and this is still 5, and this is x of t minus lambda. And you can ask yourself, okay, is this sketch acceptable? You can say, well, let me put in t equals 0. If you do, where is this rightmost endpoint going to end up? It's going to slide over to 1, isn't it, when t is equal to 0. Where's the left endpoint? Minus 3. Oh, it looks just like x of minus lambda. That's a way to sort of check your sketch with your picture, with the expression that you're using for x of t minus lambda. Wow, we've done the flip and slide. Okay. Now what we want to do is put these pieces together underneath the integral. And what we're looking for now are in fact distinct overlap patterns. We are going to move x of t minus lambda, we're going to slide this waveform through h of lambda for various values of t. And we want to know, when do these overlap patterns look distinct or different? That's the next step in this convolution process. So now what I'm doing is I'm going to look at particular overlap patterns. And the very first overlap pattern is actually no overlap. And by overlap, I don't mean that the waveforms themselves have to overlap. It's their interval of support that overlaps. Let me see if I can. So no overlap of the support interval. What I'm meaning is, suppose that I now have a curve that looks like this. And I'm going, whoops. I'm going to crosshatch that this way. And my crosshatching is crosshatching the interval of support, where that waveform is non-zero. And it could have been negative, that waveform, and that crosshatch would be the same place. Now compare, or look at that relative to this waveform, and now this waveform has an interval of support that I'm hatching with blue. Now those waveforms, a lot of students get confused. They say, well, the blue is not on top of the red. It's negative. Well, don't worry about the signs. You're interested in where you have a crosshatch. Where is the red and blue? Where are they overlapping? That's the interval of overlap between those two waveforms. This is what I'm meaning by overlap. They don't have to both be positive or both be negative. Their interval of supports need to overlap. Now I'm saying, let's look at the first overlap pattern where there is no overlap, and you can immediately draw h of lambda. H of lambda was this. This was now h of lambda equal to e to the minus 2 lambda. And now we're sliding t, we're varying t to establish unique overlap patterns. And we're starting t very far to the left to try to make sure that, oh, is there a non-overlap location or value of t? Let me now write down x of t minus lambda. It was 5. This was t plus 1, and this was t minus 3. And now I have this maybe I should have done this one in red, but do you see that this one just keeps going and going? But now, do the intervals of support overlap? No. And when do you see this overlap pattern? Hopefully you can see that as long as this edge of x, of t minus lambda, which is t plus 1, as long as it stays to the left of lambda equals 0, we have this picture. We have no overlap. And this is forming the integrand of our convolution. And what's y of t going to equal if h times x of t minus lambda, that product produces nothing, does it? So the output is 0 as long as you have this pattern. Question?
For this case, h of lambda, do we consider anything past 5 tau to be a support interval, even though we consider it to be basically 0?
So the question was, how do we, how much of h of lambda do we consider? Analytically, you consider all of it. So it's going from 0 to infinity. I'm kind of giving you a practical feel when I say 5 tau. So in reality, you might say, well, after 2.5 seconds, this is done. But on an exam, I'm not wanting reality. I want analytical. So I want you to say, oh, h goes from 0 to infinity. That's what I'm expecting you to do. But in reality, yes, after after 5 time constants, it's going to be negligible. But now you just told me that y of t is equal to 0 for what values of t? This is where the overlaps and limits come into play. This is the second piece of the convolution process. This y of t equal to 0 occurs when what? Well, I just said as long as t plus 1, which is this guy, as long as that stays to the left of 0, I have no output appearing in that convolution integral because there's nothing, when I form the product of h of lambda with x of t minus lambda, there's nothing. And you can now translate that inequality expression into, well, just subtract 1 from both sides. And you say, oh, as long as t is less than minus 1, I'm not seeing anything. And is that what we said before? We said if we apply an input at t equal to minus 1, when do we start seeing it? We didn't say minus 2. We didn't say minus 5. We said, oh, it's going to happen after t equal minus 1. So this is consistent with what we expected. We shouldn't see an output before t equal minus 1. So here's the very first answer that we can write down. We're going to have many different pieces to this answer. Y of t is equal to 0 as long as t is less than minus 1. If you want some points, you can at least find this case, I hope, on the exam, is the no overlap case. What if we have partial overlap? Well, now it's just a function of sketching this. Here is h of lambda. That hasn't changed. This is now h of lambda. This is 2 e to the minus 2 lambda. This is lambda. And now, I'm probably changing up the colors, I apologize. This is now t plus 1, and this is t minus 3. This is now our x of t minus lambda, and this is our h of lambda. And it's important how I'm cross-hatching these. That's going to give us information as to how to compute this convolution integral for this overlap pattern. When does this overlap pattern occur? That's the first thing we might want to think about. This overlap pattern of partial overlap occurs. And now you're simply looking at these sides of x of t minus lambda and trying to figure out under what condition do I have t plus 1, that side overlapping h of lambda, and this left side not. That's the unique part of this. What do we need to have happen for this overlap pattern to exist? What's the first thing that you'll say relative to this pattern? This was as long as t plus 1 stayed to the left of 0. Now what are you saying? As long as t plus 1 slides through 0, we're going to start to see that partial overlap. So the first thing we say is we want t plus 1 bigger than, and I'm going to say bigger than or equal to 0. I like to sort of have one side of my inequalities greater than or equal to or less than or equal to, and the other one an inequality. So we need t plus 1 greater than or equal to 0, and to keep it partially overlapped, we need a second condition, and do you see that t minus 3 needs to stay to the left of 0? So we have t plus 1 greater than or equal to 0 and t minus 3 less than 0. We need those two playing together. And if you solve those for t, you can hopefully see that, oh, t needs to be bigger than or equal to minus 1. That comes from that one. Just subtract 1 from both sides and you see t is greater than or equal to minus 1. And now this one says, oh, and t is less than 3. I've just combined those. So now for time between minus 1 and 3, I have this overlap pattern. Now you want to know, well, what's y of t? What's the output? That we can now use our convolution integral to figure out. And what is our convolution integral? Now we say that we have y of t is equal to the integral. Let me worry about the limits in a minute, but the argument is x of t minus lambda, which is 5, times h of lambda, which is 2e to the minus 2 lambda d lambda. That's x of t minus lambda, h of lambda. Now let's figure out the limits of the integral. Well, that's going to be determined by all this cross-hatching. If you now wanted to find the area under the product, so we're multiplying h of lambda by x of t minus lambda, that is our integrand. What are my limits? Well, it's only going to be from 0, where it's cross-hatched, up to t plus 1. That's my upper limit. Those determine my limits of integration. It's not, do you see that I'm not integrating from minus 1 to 3? This is where people a lot of times confuse things. The limits, the overlap is true from t equal to minus 1 to 3. The limits on your integral are from 0 to t plus 1, not minus 1 to 3. Intervals and limits. Intervals and limits, they're different. I'm trying to make that point. So what did I just say? We're integrating from 0 to t plus 1. Now I'm assuming we're okay to integrate that because of time, and I'm just going to write down the result. You can do this tonight at home. I know you're going to run home and do these integral problems. The integral is going to be the same for all of these steps. It's just evaluating at the lower and upper that's going to be different. But now, if you did that, you would find that this is now 5 times 1 minus e to the minus 2 t plus 1. And when is that functional form for the output true? Is that from 0 to t plus 1? When does it occur? It occurs from -1 to 3, doesn't it? So this y of t that we just computed is valid over this time interval. Different from our integration limits, but it's true for t between -1 and 3. What is it below -1? Y. That was the no overlap. That was 0. So we're getting pieces of this whole coming together. This is now a second answer, and that's the partial overlap case. In this particular problem, we actually have a total overlap piece. Here's H. And so this is now H. And now we're saying that these two waveforms are totally overlapping. Well, then that t minus 3 needs to slide through lambda equals 0. We now need this to be the case. This was t plus 1. This was t minus 3. And this was x of t minus lambda, which was constant. And when does this overlap pattern exist? So we need to find the values of t when this overlap pattern is true, or when it exists. And that's going to be different than our limits of integration, generically. This occurs, this pattern, when t plus 1 greater than 0? Yeah, but that's not even active, really. It's t minus 3 as long as that slides through 0. So this occurs when t minus 3 slides through 0, and then it's always like this. Looks the same. We have total overlap, and this gets back to your 5 time constant question. This happens forever. When can you quit watching? Probably after the exciting part in 2.5 seconds, after it finishes, right? And we're going to figure out when that is. But here, this occurs when t minus 3 is greater than or equal to 0, or when t is greater than or equal to 3. And what do we have? Now we need to find out what y of t is during this exciting time for t greater than or equal to 3. Y of t is the integral of x of t minus lambda times h of lambda d lambda. That's what we're evaluating. And now we need to evaluate the limits of the integral. Is it 0 to infinity? Where do we have an overlap of x of t minus lambda and h? Between these two limits. The lower limit is t minus 3, the upper limit is t plus 1. That's our limits on our integral for y of t. We now go from t minus 3 to t plus 1. And when you're doing this, do you see that the integral here in this total overlap, evaluating that is exactly the same as evaluating this integral. It's just we have to evaluate it at two different upper and lower limits. But once you've done the integral, you've worked through the hard part. Now you need to worry about evaluating it at different points. I'm going to let you do that. I know you're dying to do that when you get home tonight, so I'll leave that for you. But now y of t is going to be 5 e to the minus 2t, and you can write this many different ways, e to the 6 minus e to the minus 2. It's a weird way to write it, but why did I write it that way? Because now that e to the 6 minus e to the minus 2 is just a number. And it's scaled by 5. That's just a number. And then I have an exponential decay of e to the minus 2, t. When is this y of t expression true? As long as t is greater than or equal to 3. So from 3 to infinity, right? This is going to be what y is. This is true for t greater than or equal to 3. And now you probably want to wrap all of this up. Clean it up into an answer. And you might say, okay, this now is y of t, and how many parts do we have? Ooh. We have 3 different parts. We had one part that was nothing. That happened when t was less than or equal to minus 1. Then it was 5 times 1 minus e to the minus 2t plus 1 between minus 1 and 3. And then beyond 3, it was 5 e to the minus 2t e to the 6 minus e to the minus 2 for t greater than or equal to 3. Yes? The question was, where did this come from? That inequality or equality. This convolution is a continuous process. So in fact, if you evaluated these functional forms at minus 1, it better be giving you the same answer. So you could have said t less than or equal to minus 1, or here to kind of preserve my equalities and inequalities, I might say the first one is for t less than minus 1. And then here, if y of t is continuous, if you plug in minus 1 here to this middle expression, what do you end up with? You have e to the minus 2 times 0. E to the 0, 1. 1 minus 1, 0. So that's 0 at t equal minus 1. You evaluate this middle one at 3 and the bottom one at 3. It's a way to check your work. They better be the same. Okay? Now, you're looking at that and you're going, what does that look like? What in the world have we produced? What offspring do we have here? We have a low-pass filter and we have a pulse. We've low-pass filtered a pulse. Oh, come on. I've already sketched it, haven't I? Yellow and blue. Let's see if that's in fact the case. This is what we have. Suppose now that we try to sketch that. Here's probably where you need your seatbelts if I'm trying to sketch this. But it's really not that difficult. What is our time constant? 1/2. So how long do we have to wait until we're basically at a steady condition? 5 tau, which is this case 2.5 seconds, right? So just thinking of this, we hit the system at minus 1. Then how long is it going to take? When does it start moving? Y of t at minus 1. And how long is it going to take before we kind of reach a steady value? 5 tau, 2.5 seconds. So minus 1 plus 2.5, 1.5 seconds, we're going to be pretty much at a final value. And wait a minute, our pulse went all the way to 3. What did I just say? At 1.5, we're almost where we need to be. And what are we going to be at a limiting value of 5, 1 minus e to the minus 2t. We're going to be at 5, aren't we? So we're going to be at 5, roughly, at 1.5 seconds. That's 2.5 seconds beyond minus 1. Is everybody following what I'm trying to say? And then what happens? We stay at 5 until they shut our pulse off. They shut it off at 3, didn't they? They turned it off. Then what do? We're an RC circuit. We discharge. And how do we discharge? Exponentially. And what's our time constant? That hasn't changed, has it? It's 1/2. How many time constants do we have to wait until we... 5 time constants, which 5 times 1/2, that's 2.5 seconds. So when can we quit watching this exciting shape? 2.5 seconds after 3. 5.5. So we start something at minus 1. And then we're moving until 5.5. So that's what we have to sketch. And what does that look like? We've now low-pass filtered a pulse. We have this. There's t. X of t looked like that. This was x of t. And what did you just tell me? We said that after, or when we reached, or 2.5 seconds after minus 1, we were basically at 5. So we should be right about here at 1.5. Meaning we should be going up like that. And, I mean, we're within 1% of that. I'm kind of exaggerating it. And then what happens? Then we wait 2.5 units of time, 5 tau, and we are pretty much done. Isn't that pretty? We have a shark fin. But isn't it kind of like the pulse? Can you sort of see a pulse? Kind of, This is now y of t with h equaling 2e to the minus 2t. That was our low-pass filter. In fact, with s equal to minus 2. We had a pole at minus 2. That's our low-pass filter. So now if you're looking in the S-plane, you would have a pole at minus 2, and that would produce this impulse response. If you had a faster filter, a low-pass filter that had a bigger bandwidth, its pole now is at minus 10, where would you expect to see that curve relative to the blue and the red? If you're passing higher frequencies, is the next curve, what color am I going to draw it in? Let me use black. Is it going to be closer to the red or closer to the blue if my low-pass filter now has a bandwidth of 10 radians per second? Show of hands. Who's brave enough to answer? So you pass higher and higher frequencies with a low-pass filter of 10 versus a low-pass filter of 2. So it should pass higher and higher frequencies, which means we should not round as much as we did with the red. So it's really going to be closer to the blue, let's say. Or we now could say, oh, and if I have e to the, so now it's 10 e to the minus 10t. What's my time constant? 1/10. How many of those do I have to wait before I'm reaching a steady state? 5. 5 times 1/10, 1/2. That was my time constant before. Now, if I hit something at -1, I just have to wait half a second, and I'm up to 5. So if I could draw that, I would be right there. So now I'm doing this. That's supposed to be an exponential. Do you see that? And what happens when we shut down at 3? We're quick, aren't we? We have a wider bandwidth low-pass filter. We're passing higher frequencies. Now, how long do we wait for this excitement to end? 5 tau. But now tau is 1/10. We only have to wait until here. 3.5. So this curve is for a low-pass filter with s equal to -10. Everybody getting this? If we now needed to sketch some of this stuff, you've already said that the time constant in the low-pass filter was 1/2. We had a pole at -2. So if you now wanted to plot these, wow, you can do better. But here's the S-plane plot. What color was I? So the low-pass filter there was -2, and the other one, which was the low-pass filter that had a higher bandwidth, I hope I put 10 tick marks here, it was there. Those are two different low-pass filters. One has a bandwidth of, or its omega is 2. The other one has a bandwidth of 10. If you now wanted to sketch these as a frequency response, what would they look like? What is the h of j omega? And now I know what you're seeing. You're seeing elephants and giraffes, everything under a big top circus tent, aren't you? For h of j omega, you're looking at the magnitude of that in dB. And I had red and black, so let me make my 0 dB line there. There's my log of omega. And relative to both cases, I have 2, and then I had 10. Where's 1? I'm on a log of omega scale. So now if I put a 1 here, that 2 better be about 30% of the distance between 1 and 10, is it? If you took the log of 2, what do you have? Log base 10 of 2. I don't know. You expect me to know that? Yeah, you guys are just full of all this data. You take log base 10 of 2, you get 0.3. So that's 30% of the distance between 1 and 10. If you look at the log of 5, then if you said 5, it's going to be a value not half the way between 1 and 10. It's going to be closer to 10. So now we've divided our horizontal, our frequency axis up into log of omega units. So that now if I wanted to put 100 on this, where would I mark it? Where would 100 be? It's to the right of 10. How far to the right? Exactly the same distance 1 is to the left. So this, if I could do that, what do I have? 1, 2, 3, 4. There's 100. Where is point 1? 10 to the minus 1. It's the same distance to the left of 1. So now there's 0.1. Do you see how many frequencies I can get on this page since I'm doing a logarithmic frequency axis? And if I'm plotting in dB, now I've taken the logarithm of my magnitude and I can plot things as straight lines. What's the low-pass filter of this guy look like that has a pole at -2? Well, if this was h of t, if I Laplace transform that, what do you get? If you Laplace transform 2e to the minus 2t, 2 over s plus 2, isn't it? So now we know that this guy is 2 over s plus 2. Is that written in pole zero form or time constant form? You can explicitly see the pole, can't you? It's at -2. That's pole zero form. If you factor that pole out, you can write it in time constant form. And now these two cancel, and you're left with 1 over 1/2 s plus 1. The time constant was 1/2, and it's scaling s. And what's this guy at s equal to 0? What's the value of h? At dc, that's when s is equal to 0. When s is not moving, s is dc, s is equal to 0. That's the dc frequency. We're right at the origin if we're standing underneath the circus tent. That's dc. Constant. Nothing. Right? That's dc. What's h of 0? Plug s into s equal to 0 in either of those, and you better get the same answer, unless we factored something wrong, and we didn't. We get 1. So now in dB, what is 1? Log of 1? 0. So we have 0 dB at dc. That means you put something in that's a constant, you're going to get that constant out because the amplitude is 1. Remember, we're saying y is h times x in the frequency domain, and we have a dc gain of some constant. What in the world is he talking? So what I'm trying to say, where is 0? Where is 0 on this curve? Good luck! You're never going to get there, are you? On a logarithmic scale, you're never going to get 0. Do you see that? You're just going to get 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. You'll never hit 0. But it's small enough. Where are we? What's our red line going to be for h of s? When s is small, we said we had a gain of 1 in absolute sense, which is a dB of 0. Oh, then we're going to be right here. And then what happens? At 2, we've agreed that this is where, whoa, now we're on the circus tent. We're up at J2. And I look back at that pole, and I do have exactly the same vertical distance as horizontal distance. We said, okay, now's where we say the imaginary part is starting to be influencing the magnitude. And now we just roll off at 20 dB per decade. And if I now said, oh, if that's the case, then here is 20. And I better be down at minus 20 dB. at that point. And I just keep going. That's my low-pass filter for the red one. What was my other one? I'm assuming you guys are so excited, you're as excited as I am, that you don't even know what time it is. Oh, ooh. So what's H of S? I'll finish. I didn't realize how late it was. Whoops. H of S for the faster is that, right? And what does its curve look like? Well, it's like this until where? Then it goes to 10, and now it starts, and then at 100, it's down at 20 dB, so that dot's supposed to be at 20 dB. And that's the low-pass filter for a filter that has a wider bandwidth. It doesn't start filtering until, in this straight line approach, beyond 10. So now what have you seen? You've seen a lot today in just this example, convolution. You have transfer functions, you have convolution, you have Bode plots, you have pole zero diagrams. It all needs to just start gelling in your head. We'll pick up at that point next week.